Now in this lecture we will discuss about addition-elimination mechanism. On benzene ring, nucleophilic aromatic substitution reaction takes place by two mechanisms. One is addition-elimination, another is elimination-addition. So we have nucleophilic aromatic substitution. One mechanism is addition-elimination, another is elimination-addition. If you see, in both cases the final product we have substitution. So we have added first, then we have eliminated. So basically we have substitution, in this case elimination first and then we have added. So this is substitution. So both a step is substitution. So we can say there are two ways to do the substitution. First add, then eliminate, or eliminate first and then add. Now in this lecture we will discuss about addition-elimination. If a halogen group is attached to the benzene ring and if it reacts with a nucleophile, it looks like this leaving group will go, but this reaction does not take place. So in this case we have no reaction. But if electron withdrawing group is attached, in the benzene ring, in that case this reaction takes place, and this electron withdrawing group should be at ortho and para position only. So electron withdrawing group should be at ortho or para position, or we can have at both position. In another case, electron withdrawing group can be at both the position. That is ortho as well as para. Now why only ortho and para, why not meta? This can be answered by looking the mechanism of this reaction. So what happens? When a nucleophile attacks on this carbon, at the same time this electron pair comes here. So we have this as intermediate. Now we have electron withdrawing group. This shows position of electron withdrawing group is not fixed. Now any factor that will stabilize this intermediate will make a reaction to proceed with a faster rate. So we want to stabilize this intermediate. A stability of intermediate will increase the rate of substitution. the rate of substitution. Now let us try to attach electron withdrawing group at ortho position, para position and meta position and see which makes this intermediate more stable. To look this, let us write resonating structure of this molecule. So we have negative charge here. Now if I attach electron withdrawing group at ortho position, at the same position, and we have a negative charge, we can write more resonating structure. We can write another resonating structure. Now if you see, this resonating structure is highly stable because electron withdrawing group pulls this electron and makes this resonating structure more stable. So this resonating structure is more stable. So this is a more stable resonating structure. Now let us say if electron withdrawing group is attached to para position. Same thing will happen in this case. This goes here and this goes here. So there is a negative charge on this carbon. We can show this negative charge here. Another resonating structure we will have. This goes here and this goes here. Now in this case again, this resonating structure is very stable because negative charge is directly pulled by the electron withdrawing group. It can be pulled by resonance or it can be pulled by inductive effect. So negative charge gets stabilized by minus I or minus R effect, that is electron pulling by inductive effect. Minus I means electron pulling by inductive effect, and minus R means electron pulling by resonance effect. So in this case, this resonating structure is very stable because negative charge gets stabilized by the electron withdrawing group. So this resonating structure is very stable. Now let us say if I have a electron withdrawing group at meta position. So we have this intermediate. This is electron withdrawing group. we can write resonating structure. Basically this bond should be here. So if I do this, we will have X nucleophile. Here we will have a double bond, electron withdrawing group, and negative charge is here. Another resonating structure we can write. So in this case again we have three resonating structure, but none of the resonating structure has negative charge on the carbon that is attached to the electron withdrawing group. So this carbon does not have negative charge, does not have negative charge, does not have negative charge. So in this case we can say none of the resonating structure has negative charge on the carbon that is attached to electron withdrawing group. That is EWZ. So none of the resonating structure is stabilized. So no resonating structure is stabilized by electron withdrawing group. So now we can say in case of ortho and para we have two resonating structure, this one in case of ortho and this one is in case of para, that is stabilized very strongly. So we can say if attack happens on a carbon that contains ortho and para electron withdrawing group, this will be stabilized. So this means on benzene ring, if I want to have nucleophilic substitution reaction, let us attach electron withdrawing group NO2 and we can have a nucleophile. We will have this reaction. But if nucleophile, if electron withdrawing group is attached to the meta position, this reaction will not take place. Now if electron withdrawing group is attached to the para position, once again we will have nucleophilic substitution reaction. Now a question can be generally asked, which of the following compound is more reactive towards nucleophilic substitution reaction? So let us say this is 1, and this one is 2, so question is arranged in the decreasing order, arrange 1, 2, 3 in decreasing order of reactivity. Nucleophilic aromatic substitution reaction. So we have to find basically which of the ring is more deactivated. and a ring that has more number of NO2 group is more deactivated, and deactivation takes place from ortho and para position. So this ring is most deactivated, that is most reactive. The second one is less deactivated, so this is second and this is third. Then we will have second one is more reactive and third one is least reactive. So more number of NO2 group at ortho and para position will make the ring more reactive. Now if I have to compare, let us say we have X, we have NO2 here, so we have to compare in decreasing order of nucleophilic aromatic substitution. So we have to write in decreasing order of nucleophilic aromatic substitution reaction. In this case we have nitro group attached to the ortho and para position. This ring is most deactivated, so this is most reactive. This one is 1NO2 group attached to ortho position, so this is next reactive. This one is very less reactive because NO2 group is attached to the meta position. A question can also be asked, one time let us say we have chlorine, NO2 group is attached, one time we have bromine, another time we have iodine, and once again we have to arrange this compound in decreasing order of reactivity. So you see, in this case we have to see which one is the best leaving group. Iodine is the best leaving group, then bromine, and then chlorine. So third one is most reactive, then second one, and then we have first one is reactive. So let us now summarize the mechanism again of addition elimination. So first part, if I have a nitro group attached to the ortho and para position, let us say X, or we can take Cl, and nucleophile let us say we have OH minus. So in the first step we have addition step. So we have chlorine, we have OH. So this step is addition. Next step we have, so this is not aromatic, so this compound is aromatic, but this is not aromatic, less stable, this one is more stable. So benzene has lost its aromaticity. Benzene wants to regain its aromaticity, and this can be done if it somehow loses one chlorine, that is elimination. So it has chlorine OH. This lone pair forces here, or basically pushes chlorine group to regain its aromaticity. Now this compound is again aromatic. So you see, the first step addition, that is loss of aromaticity, and the second step elimination, that is gain of aromaticity. First step will be slow because in this case we have loss of aromaticity. So this is a slow step, and rate determining a step. The second step is fast step because in this case we are gaining aromaticity, so this is more stable compared to the reactant that is less stable. First part will be endothermic, that is addition step will be endothermic. So delta H for this part is positive. But for the second part delta H will be negative. Because we have more stable, initially we have less stable. In first case we have more stable, finally we have less stable. We can also make a potential energy diagram for the same reaction. So let us say we have on y-axis we have potential energy, on x-axis we have reaction progress. So initially we have reactant here. The first step is slower step, so it will have high activation energy, and finally we will have this. Here we have intermediate. This is first transition state, this is second transition state, and this one is intermediate. Here we have reactant, and here we have product. Intermediate is this. So we have chlorine. In this case we have taken nucleophile as OH. So this is intermediate. We can basically show transition state 1 and transition state 2 also. In case of transition state 1, this carbon OH bond is slightly forming, and this carbon-carbon double bond is slightly breaking. So we will have carbon OH bond is slightly forming, this bond is completely, and this bond is breaking. OH will lose some negative charge, and this carbon will regain some negative charge. So this is transition state 1. Similarly we can write transition state 2. In case of transition state 2, we are forming a bond here and we are losing a carbon chlorine bond. So we are losing a carbon chlorine bond. OH bond is complete, and we are forming a bond here. So this is basically breaking, and this is forming. Chlorine will have delta negative charge, and this will also have delta negative charge. So this is transition state 2, and this one is intermediate. If you see, the final product is substitution. So what we have done, we have initially NO2 group is also here. Initially we have this compound Cl NO2, and if this is reacted with NaOH, finally we have removed one Cl and we have added one OH. So final reaction is substitution. The first step of reaction is attack of a nucleophile, and that's why this is called nucleophilic addition reaction. So first step is attack of a nucleophile, that's why it is called nucleophilic substitution reaction. Mechanism is addition, because first step is addition, next step is elimination. So in this lecture we have discussed about nucleophilic aromatic substitution, addition elimination mechanism. First step is loss of aromaticity, second step is regain of aromaticity, and we also said if electron withdrawing group is attached at ortho or para position, it increases the rate of nucleophilic aromatic substitution. Nucleophilic aromatic substitution is also called SNAr reaction. So this kind of reaction is also called SNAr, that is aromatic nucleophilic substitution. So this is for aromatic, and N is for nucleophilic, and S is for substitution. So nucleophilic aromatic substitution is also called SNAr kind reaction. So addition elimination mechanism is also called SNAr mechanism. So you see, addition elimination mechanism we have. So this mechanism is also called SNAr mechanism. The elimination addition mechanism is called benzene mechanism. Benzene mechanism. We will discuss this also sometime later.